Hello everyone, my name is Amrit, and in this video I'm going to tell you a little bit about the research that I do. Our universe is made of matter and energy. Most of this matter, however, is in the form of dark matter, which is to say that we really don't know what it is. Now, because it's dark, it doesn't emit light and it doesn't react with light in any way, we can't really see it. But we can use the technique of gravitational lensing to study dark matter. This is where Einstein's theory of general relativity helps us. And lensing states that anything with mass, can bend the path of light. See, if you look at the image here on the left, the light from the red distant galaxy gets bent by the much closer blue galaxy. And what we see with our telescopes is multiple images of this red galaxy smeared out. So you could imagine that lensing works sort of like looking through a magnifying glass. And this tells us something about the distribution of mass along the light rays. Now, there's many candidate particles for dark matter, although we don't really know what it is. And the conventional model is what we call WIMPs, or weakly interacting massive particles. Now, as the name suggests, these are just massive particles. And of course, there's alternative models. For example, very light particles or axions. Now, as you can see from the scale here, WIMPs are still the traditional candidate for dark matter. But despite decades of searches and billions of dollars of funding, laboratory experiments are yet to find a WIMP particle. Now, this signals that it's high time that we start looking at other candidates for dark matter. Now, gravitational lensing in astronomy produces these spectacular images that you can see here, forming all sorts of different configurations. You can see the background distant galaxy as these blue images, sort of like arcs, and the much closer yellowish galaxies, which are acting as the lenses. Now, when you use the conventional WIMP dark matter to make models for the distribution of mass in these galaxies, what most of the time modelers find is that they can't really reproduce the observations. They can't reproduce the positions and the brightnesses of most of these images. This is where my research comes into play. We look at a new contender for dark matter called wave dark matter, which is made up of very light particles. Now, in 2014, our collaborators did the first simulations of wave dark matter, and you can see these beautiful interference patterns that are being created because wave dark matter, as the name suggests, acts like waves and interferes, much like waves on a beach. Now, almost a decade later, our research, published in Nature Astronomy, finds that models made of wave dark matter are able to reproduce many lensing observations, which WIMP models struggle to reproduce. What we propose to do in our research is to extend our work that we did on individual galaxies to galaxy clusters. These are the most massive objects in the universe, and as you can see, the lensing here is much more complicated. Now, these clusters also exhibit anomalies in lensing, and we hope to see whether wave dark matter can resolve these anomalies. That would help us shed light on the nature of dark matter and guide us towards the correct direction for new physics.